Mega Mechatronics.
Welcome back to Mega Mechatronics. We are continuing our materials engineering series, and we are going to talk about surface finish. The surface of a material is the boundary of that material, where it meets another material, or it meets the atmosphere, whether it's air, or a liquid, an oil, all kinds of things. So that is physically how the shape appears as it is the boundary of the object. So looking at a part like this, you can, this is a CAD model obviously, you can imagine through the manufacturing processes that you are thinking of using when building the part, you could get a sort of an idea of the big surfaces being shot peen like this, where you would clean it up, and the edges, let's say you cut it out with a CNC plasma cutter, the edges would look something like this, or similar depending on the technology, if it was a laser cut or used a plasma jet style of a cutter. And here you could see a little bit more complicated system of a linear bearing system. You see there's tiny ball bearings, and those are highly polished, probably plated with a very hard material, a very extremely good surface finish. You can see they almost look chrome, they're reflective, and those are riding on another very highly polished rail system. And some of the other components don't have critical surface finishes, but the portion where the bearing, the boundary of the balls, where they meet the boundary of the rail, need to be pretty tight in specification if you want a really smooth rolling and long-lasting bearing system that can hold a lot of weight, take shock, things like that. So characteristics of surfaces, first we have the lay, and that's the direction of the pattern of the texture of that material, of that surface boundary. So you could see a couple images there where the one pattern has a sort of laying 90 degrees from each other, straight lines, and then this sort of milling process. There's a lot of chatter marks and things like that in that, but you can see they used a rotating tool, you can sort of tell. And on the other side looks more like a some sort of grinding or polishing system that was not rotating in a circular motion. And then we have roughness, and these are the micro irregularities. So the very small bumps you see in that red line would be something like roughness, but then that's combined with waviness, and these are the macro irregularities. So that's that sort of wave pattern that you can see between the micro irregularities and the macro irregularities. And then we have flaws, and these are discrete irregularities. This is something that's not in a pattern. There is no pattern to these flaws, and the flaws could be defect in the material, contamination, tooling marks, something went wrong with the process, possibly a tool broke, and things like that. So these are sort of singularities or discrete occurrences. So looking at surface lay, you can see there's actually a couple different surface lays here. One is more of a sort of like a ground surface on the bottom, and then you see those really nice lines on that part sitting on top of that table. You could see those very straight lines, those parallel lines, and that's something probably CNC ball milled or something, a process like that. So those are pretty big waves, and in those waves or within the waves are going to be a roughness feature. And then looking down here, we have this part with sort of that circular pattern. We would assume that this part was probably a fly cut on a mill or something similar. And then looking at this knife blade, we can probably conclude that this was ground based on those straight and parallel sort of random looking marks. If we were to zoom in, we would probably see something like this. So they're not exactly parallel because it was probably done by hand, and it would be difficult to ensure it is precisely perpendicular to the grinding system, but you get the idea. And looking at a crankshaft here, you can see the journals are highly polished, and that's actually very important. That surface and how you finish that surface, because there is this attribute called fuzz when you polish these crankshaft bearings, and depending on the direction of polish, you're going to actually kind of fold that material over and create this sort of fuzz, what they call it. So that the picture is a cross section of that shiny journal, and it's that direction of that, it's very important. So you need to know the direction of the crankshaft, how that's going to operate, and you can see how that is spinning in a clockwise manner, and how that fuzz is not creating any friction or excessive sort of like a scraping action. So in this way that they have it orientated, it's going to reduce that scraping action on that bearing, increasing the service life. So looking at surface roughness, which can also be surface texture, surface topography. But we'll say surface roughness, some attributes. This is the micro irregularities, and we have our peaks, and you can see that tall peak over there, that is a peak as well. And then we have our valleys here for these micro irregularities. So this is probably an important thing that we need to cover when looking at surface finish, because this topic goes very deep, as I'll show you later, the different types and parameters or ways of quantifying surface finish. There's a lot of different techniques. So looking at the bearing function of a bearing and how surface finish relates is, when we're looking at a bearing surface, we want something that's really low friction and really low wear. So you can see in this small picture here, that's almost a mirror polish. And from my experience with the GM Atlas engine program, it was some pretty awesome technology. I was on the floor there about 5 years after they launched it, and they had a little display with the i6 lined up there. And to demonstrate their manufacturing capabilities and the design, and in particular the finish of that crankshaft, they assembled a sort of a engine block with the crankshaft sitting in there. They put 1 drop of oil in each journal and then sealed that up as a display, and they had a little hand crank on the end of the crankshaft, and when you crank that thing would just spin around. It was such low friction, and it was sitting there for 5 years unserviced, and that just goes to show the technology they put into it, and the capability and design of that engine, and how low friction that was, and that translates into better efficiency and more power potential. And now we're looking at conduction, so conduction of heat. And in this, we need to maximize the surface area, so we need to minimize those peaks and those valleys. And you see in the picture there is probably a computer heatsink that has been polished extremely to a very fine polish. And you see it's almost like a mirror. That's how smooth that surface is. and that's going to improve the heat conduction and reduce the amount of thermal paste you need to use, because that thermal paste is not as good of a conductor as the copper or that base material. And decoration, and this is a consistent light reflection. So you see here is sort of like a stainless steel. You may have seen this in a nice fancy elevator or something in a hotel, but there are other surface finishes, whether it's polished, a shot peen sort of dull look, and things like that you need to consider. Even with non-metal materials, that's very important with plastics and things like that. Adhesion. So you see someone here is repainting their car, and he's going over it with a Scotch-Brite pad, and he's roughing that surface of that base material, or that old paint. He's going to have to rough that up because the surface is too smooth to ensure maximum adhesion of the new layers of paint that he's going to apply to the vehicle. So that roughness is sort of acting like an anchor for that new coating, that paint coating he's putting on there. And friction. What we want the surface finish to look like is to have sharp peaks and lower contact area. So in our little example here, we have a performance clutch plate that has been sintered. It started off as a metallic powder that was baked, and you see that surface is actually pretty rough. And that's going to create sharp peaks, those little granules of metal that went into the sintering process, and those peaks lower the contact area. In addition, they created these quadrants to further reduce that contact area and increase the pressure that this particular plate can produce. And obviously, this was for high performance applications. And sealing. And this is also important, the contact area, and we want a low wearing surface, so typically it's going to be a smooth surface. And you can see here is a little overview of a rear main seal on a crankshaft of a vehicle and some ways that leaks happen. You can see a groove wore into it, and that's pretty normal. And you can actually repair that by getting a repair sleeve that you install over that with a slightly oversized rear main seal, and you can fix that up. I've done that before. And in the middle there's pressure distortion from improperly torquing the flex plate to the crankshaft or the flywheel. And that can actually cause distortions, which will cause leaks in areas where when that crankshaft is spinning, the rubber seal is not flexible enough to close those gaps just from the inertia of the seal being open and closed so quickly. And then obviously cracks can cause leaks. So looking at these parameters, you see there are so many parameters, and I believe there are more parameters than this. The popular ones you probably heard are RA and RZ, but we're not going to get too deep into this, so don't worry about it. So we can visually do a pretty good job by visually indicating surface finish. So let's look at these blower bonnets, and you can tell on the top one here is sort of, it's kind of shiny. It's not rough, but it is a little dull. So we can sort of assume that it's not exactly rough, but sort of in between. The peaks and valleys are smoothed out. So maybe something like in D there, delta D. But then we have this very highly polished one, and these are both aluminum. And you see that this polished surface, that mirror finish, is very, very smooth. Something like you'd see in that F image there. So how do they measure surface finish if you don't have a electron microscope? Well, it's based on a stylus system. So the stylus is transversing across the surface, getting pulled across the surface, and that stylus is hooked to a very, very sensitive measuring device that will measure the peaks and valleys as that moves across and plot that out for you. And a lot of these will do all the math for you and averaging to give you those output those parameters. So you can see in these that stylus is being pushed or pulled across, and that stylus is going to move up and down. If you imagine the drive unit is static or stable and not moving, same with the cross section or the material, and the stylus is going to move across and move up and down, and that's what we are measuring. So what a measurement would look like is something like this. So up at the top, if you can visualize, it's a section of a 3D section, but what we are measuring with the stylus is a 2-dimensional section of that 3-dimensional piece. And you see that flaw there, that would be like a discrete irregularity. So there's only one of these in this part possibly. And that could be from someone dropping something on it and crushing that down or something like that. So if we look at the total profile, this includes, this is basically the raw output of that. So you could sort of match up the peaks and valleys from the 3-dimensional part down to the profile. And from that we can derive the waviness profile. So it's filtering. We are filtering out the roughness or those micro irregularities, and we are looking at the waviness. And we can also filter out the waviness and give us a attenuated roughness profile that removes that waviness. So it sort of gives us a average median line, and we can line that up and get a better idea of the max and min of the peaks and valleys of that roughness profile. And you can also do a really good job using just your fingers. Your fingers are extremely sensitive, and unfortunately some blind people unfortunately people are blind and have to deal with this, but they have adapted quite well. So someone who has enhanced their senses can actually feel houses and cars. If this were to scale, if that Earth was to scale, some people will actually be able to feel a car if they rub their finger across there. Or let's say we put a car on a perfect sphere of this size, and the car is to scale with this, that person could actually find that vehicle just by using their finger. Well, that concludes our video on surface finish. Thank you so much for watching, and if you liked what you saw, please like the video, and if you want to see more videos like this, please subscribe. Thank you.